Well, congratulations. We're in our first homework of Chapter 5. We only have 3 homeworks here, and then we have 2 more in Chapter 7, and we'll be done with the course, so we're getting close. 5.1 is covering the trapezoidal rule. We'll then move to 5.3, looking at Simpson's rule, and then back to 5.2 to take a look at the Romberg integration. You'll see more of that in the lectures on why that's important. But for part A, we're going to do pseudocode again for the trapezoidal rule. And we're going to try to integrate the function f of x equals 2 sine x cosine x. I do want you to assure a relative error accuracy of 10 to the minus fourth or less. Don't actually turn this in. In fact, during this help video, or hints video rather, we are going to look at that pseudocode, so you'll have it right in front of you, and from that you should be able to program it pretty easily. Before you do, though, go to part B and we'll do the exact integration just like you were in second quarter calculus. And you will need to either use the substitution rule, where your function 2 sine x cosine x can be looked at as u equals the sine of x, and du equals cos x dx. So you could integrate it that way through substitution. Pretty easy. Or even easier is if you look up in a trigonometry book, you'll be reminded that the sine of 2x is equal to 2 sine x cosine x, and that makes it easier yet. So take your pick, whichever way you want to integrate it. It's like a one-liner, doesn't take long. We are integrating between 0 and pi over 2. So when you do the integration, do the definite integral, come up with a numeric answer, and that will be the exact value that we will be doing some comparison to in our trapezoidal rule. Part C is the main part. You'll really review the pseudocode that we're covering now and convert that to MATLAB and get the right integral within an error of 10 to the minus fourth. I mean within a relative error of 10 to the minus fourth. Don't remember, the relative error can be calculated more than one way. The way that would be the nicest, if we could do it, would be to take the exact answer minus the calculated answer divided by the exact answer and take the absolute value of that, and that would be the exact relative error. But rarely do you get to have the exact answer because most integrals can't be done, and you usually have to use this some sort of numerical method to get your result. So we can use method 2 to get our relative error by replacing the comparison or the total error between the true answer and the calculated value with using the last 2 results. You take the difference between those 2 results and then you divide by the most accurate result, which would be the last one, and then take the absolute value. So that would be method 2 of doing the relative error. So do them both, because you can in this case, and keep track of how many times you had to iterate. How many times did you go through that loop? And print that out. That's worth 5 points. Calculate the total number of terms that are in the trapezoidal rule that you had to use. Well, you'll need to build a counter in there that every time you create a new term, you count it. But be careful, because you are using the recursive method, and the recursive method makes use of all the calculations prior to it, because it had that really smart way of only calculating new values in between the grid points that you already had set up. So make sure that you not only count all the points you're calculating on one iteration, but you keep track of all those that had been done before, because the sum of that is actually the number of terms that you'll have to count. Well, we're ready to go ahead and try this algorithm and see if we can get it to work. We need to develop a final answer, which we're going to call S. Here I'm calling it S sub t, meaning sum of trapezoids at the nth iteration. But to keep it simple within our algorithm, we're going to call this whole term S. It will represent a sum of trapezoids. The n will be our recursion number, which will start with 0. Very crudely, we will take one trapezoid covering the entire interval itself and calculate its area and claim it's a very rough approximation for our integral. Well, if we're using one trapezoid, then the base of that trapezoid must be the full integration interval. In our case, we're integrating between 0 and pi over 2, but we'll just continue to call the interval a and b just to make it a little bit simpler. So we need a starting value, and that's pretty easy to do. We'll say our starting condition for our sum is going to be the entire trapezoid. Well, the formula for the area of a trapezoid is the average height times the base. Our initial base is going to be the full interval, and the trapezoid average height is the function evaluated at the low point plus the function evaluated at the high point divided by 2. So this represents one trapezoid, or the area of one trapezoid. Okay, now we just start the algorithm rolling because we have a starting point. N now becomes 1. So hn minus 1 was h0. That was our whole interval. So we take the whole interval divided by 2 and we get a new interval. In the algorithm, we'll drop these subscripts. We'll just call this h and overwrite the value of h on each iteration. Now we will take the sum of all the points that need to be added to form two trapezoids. Why 2? Well, because we cut the interval in half, so we have a lower trapezoid and an upper trapezoid. Now that means that we only have one additional point we need to calculate, and that's the point in the middle. So the question is, does this formula really accomplish that? Well, A is my low point. If k is equal to 1, then 2 times 1 minus 1 is 1. Well, our new h is half the interval size. So this expression puts the argument, which I'll later call x, to be right dead in the middle between a and b, which is exactly what I want. But that's the only point I want, so I need to make sure this sum stops. Does it? Well, n is equal to 1, and 2 to the 1 minus 1 is 2 to the 0, which is 1. So this formula was perfect. It only created one point, or the need for one point, and it got just exactly the one we want. We multiply that by our new h, add that to 1/2 what we had before, and we have the next value. Now this then gets plugged back into this position here, but h first must be cut in half again. So now we're looking at 1/4 the original interval size. And this better pick up only 2 points. Why is it? Well, because we have 3 points now. We have the low end, the high end, and the middle. So we need a point at the quarter position of the interval and the 3/4 position. Does this do that? Well, 2 times 1 minus 1, again, is 1. But h is 1/4 the original interval. So a plus 1/4 the interval is the correct x value to evaluate f. Now, does it go through 2 points? Well, if n is equal to 2, 2 minus 1 is 1, 2 to the first power is 2, so I'm summing exactly correctly. And when I plug in 2 here, then 2 times 2 minus 1 is 3, 3 times 1/4 the original h value is 3/4 the h value. So again, I'm picking up exactly the right x value to determine my f. And you can check the rest of them, but you'll see that they keep cutting each interval that you create in half, and it works very nicely. So here is the pseudocode. You can check that and literally copy this thing into MATLAB code to accomplish problem C when you get there. And here we created the full interval like we said we needed. Here we created the single trapezoid covering the whole interval. And we've set ourselves up some tolerance requirements and initialized an arbitrarily large relative error and started our n counter. This is our iteration counter. And we did what we just said we would do. We decoupled the counter number from the variable and called it n. And we cut the interval in half. This cum variable, though, is a special variable that we're setting up to accumulate that sum. Let's go back a slide for a second and take a look at it. This sum is what I am calling cum on the code. So if I set cum to 0 initially, then I better calculate in my for loop all the right positions that this formula here requires. Well, does it? It does, but it does it just a little differently. You'll notice that I set my x value to be a little bit before the interval. Okay, that h below the interval is just the perfect amount of position so that when I end up adding 2h to it, it will skip in between the values that are already calculated. It'll take each odd position. So position 1, 3, 5, and so forth. And I evaluate the function at that point, add it to what I've already accumulated, and overwrite the accumulator variable within this loop. Almost done. We just have to remember that we take whatever s was initially, and we take h times that accumulator, and we form our new s value, which then loops back around and around. Well, almost. We need to first check to see if we've met our relative error requirements. If n equals 1, there's no way we can get a relative error requirement, so we just set it to some number. Otherwise, for all other iterations, we calculate the correct relative error formula. So this is the current value minus the previous value divided by the current value. Now I'm missing a line here, it looks like. It looks like I need s previous set to s, so don't miss that when you do yours, and make sure that's okay. Somehow the copy and paste thing here didn't quite work, but you need an s previous set equal to s to make this value work correctly. So with that, we'll stop. I'm going to let you do the analytic integration for part B, and also for part C, turn this into MATLAB code, and you'll be all done.